Okay, so you want to go to the New River website. I assume everybody can get there, and then go to My New River. And they've got uh, you need your name and password. Have you been into it before, or is this your first time in? First time in. Okay, first time in. Your username is your email, the name the name that they use for your email, which would be your last name underscore and your initials. That would be your username. And then your password, before you change it to something you want, is your student number with N on the first and R on the back. Well, from your perspective, N on the first and R on the back. Okay. Then when you go in, it may even ask you to change your password. And it'll also, I'm not sure if it does it the first time, this second factor passcode, this is an added level of security. So I've got mine set up to where it'll send that passcode to my phone. And then I go in and it's just the right one. Yep. There's your portal. And you want to go to D2L. This is Desire to Learn Brightspace. That's where you'll find the course. Go to this little waffle right up here. There's a delay. Go up to that waffle, click on that, and you'll find all the courses you're registered for here. So I'm going to go into this one right here. And you'll notice several things. This is called the mini bar right up here. And for the one nice thing you can do is the class list. Hey, you can go to the class list, and there's everybody in the class. If you want to send an email to the class, or one person in particular, say, the same thing will be there for the labs. You can contact that person over the New River email and maybe get the results of a lab that you missed, something like that. Your lab partner. Or this is the way I broadcast emails, and I send emails over the New River system. So if you're accustomed to getting emails, your personal email, you won't find anything in there from me. It's all coming through on your New River email account. That's company policy. Okay. Then content is where you're going to find everything that's in the course. Everything I hand out here is in there too. The exams are set up in modules. Right, there's exam 1, 2, 3, 4, 5, 6, 7, and a final. I've kept it hidden because I'm not finished working it, but there will be a final. Okay, Zoom class meetings. This is where you connect if you have to the Zoom class. You just click on that and just follow the instructions. You'll need a camera, of course. So I won't go into that anymore. This is homework registration. Let me see what it happens when I click it. It works? Oh, okay. Okay. That's good news. You'll go in here, and the first time you click on this link, it's going to ask you to register with Cengage. They're the publishers of the textbook, and they have a homework app called OWL that I use for your homework assignments. Okay. So if you don't already have your textbook, you need to get one. And be sure that the textbook you get has access to OWL. If you buy it through the New River bookstore, then it's automatic. It's already, the ISBN number is the correct one for that. But be sure that when you register for the homework with Cengage, you do it from within Brightspace. That way, the your grade book, your grades in the Cengage homework are linked into Brightspace. So when you complete an assignment, it shows up in the grade book here. It's probably a good idea to when you buy the book and get the code, that you buy it using your New River email address. That way, the code will be linked to that address, and Brightspace and Cengage both know that you're registered in the course. Okay, because you're listed in the see, what do they call it? The list of students in that course. I can't remember the name. Okay. This link right here, course schedule and due dates, I took this straight out of the syllabus and just put it in here so that if you want to find out, if you want to go look and see what's due when and what we're going to be doing on a certain day, you don't have to go digging for your syllabus. You just click on that and it shows you all the things that we're going to do in the lecture course, 102. And then on the side, I've got this side panel with the labs that are going to be done on those days and the due dates for those, just so that it's all in a nice compact area. And this is all old stuff for 3 of you. Here's the syllabus. You just click on it, get the syllabus. There's my schedule. I gave you a copy of my schedule, so we won't have to look at that. This is where you should be able to link to the textbook. If you buy an electronic version with access to the homework, you should be able to click on this one and get to the electronic textbook. Okay, Zoom class meetings right here. We showed you that already. Now the modules. What do I put in the modules? Okay, this is, let's see, let's go to exam 1 module. I've got a checklist here. These are the things that you want to be sure you do for this exam. And notice that the crossword puzzles are extra credit. Let's see, what do I do? I take all the crosswords and average them together for 1 exam grade. Is that the way I think that's the way I do it. Isn't it? According to your memory?
Yeah.
Yeah.
They were, yeah.
Yeah. So if at all possible, I'd do the crosswords. It's an easy way to make some points. Huh? Okay, so since this exam has 2 chapters in it, chapter 10 is going to have its set of documents, and there are the PowerPoints. I give you PowerPoints in 3 flavors. If you have Microsoft Office, you can go to this one. And in fact, the more recent versions of PowerPoint and the browsers, I think will actually load those up in the browser, won't they? But if they don't, go to this iSpring down here. Sometimes I say HTML5 and sometimes it's iSpring. But this will actually open up a file in the browser. You don't have to have PowerPoint to view it. And it's got all the slides, it's got all the animations, it's got all the embedded videos. PDF is kind of it's dumbed down version. All you get is the slides and you don't get any of the animations or the videos. So that's your last ditch effort if you need the slides. Okay, and every chapter that I have PowerPoints for are set up like that. So let's see, there's a checklist, there's chapter 10 PowerPoints. Then we have a time for review, and I gave you a review document for chapter 10 and another one for chapter 11. And also with each one of those review documents is a handwritten solution to the problems. Okay, so a lot of my students take the review document, treat it like an exam. They just go in there and it looks like an exam and work it through, grade yourself, because the key is in here also. Here's, let's see, where's the key? Here it is right here. So the key for chapter 1 is right there. I don't print out a copy of that. But you grade yourself, find out which ones you're weak on, then go back and try to figure out what you did wrong and work them. And if you get to the point where you can't figure out how they work, go to that review, the worked problems, the handwritten thing, and see how at least one solution for the problem. Lots of times there are more than one ways to work a problem, but that's one way. And if you still can't get it, bring those problems to class on review day. That's in the schedule. And we'll tackle those first before I get into whatever I'm going to do. Okay, so those are all there. Sometimes there's extra information like this, how to find the edge length of a unit cell, body-centered cube. You don't know what that is because we haven't talked about it yet, but we will. Okay, that's chapter 10. Let's see, what else we got? PowerPoints review. Then there's chapter 11 set up the same way. I actually have a homework link in there. I do. There's a homework link for, let me see if it works, because I forgot I had that one in there. It should be linked to this course. Okay. Doesn't say. Go over to course. Yep, there it is. Okay, it's properly linked. That takes you directly to the chapter 10 problems. So you can either go through that registration site and then find the chapter that you're supposed to be working on at the time, or you can go into each module and click on that homework link, and it'll take you straight to that chapter. All right, get out of my way. Let's go back to content, see if there's anything else I missed. And then we'll look at the syllabus in just a minute for details. Okay. Actually, we're looking at this. You know what? I better do this as a student. I should have done that to begin with. Because you're seeing it, that's what it looks like for instructors. There we go. It's less cluttered now. There's your crosswords, right? You get copies of your crosswords there. If you lose them or the dog eats your homework. Let's see. I don't see anything else special in here. Videos. I said I record everything that happens in the classroom. At least it picks up any shared files, and it picks up me. I don't have you guys on camera. That would be, in my mind, that's a violation of your privacy. So it's just me and anything shared. So, and I post those videos, and the ones that I've done in the past, I put into this archive. What these are links. These are links to my YouTube channel, videos that I've produced in the past. And you can go look at them if you want. The older ones are probably poor quality. But the more recent ones I put out here, let's see, let's collapse that. I put those out here with the other folders. Right. So if you see it out there and it'll have a date on it, you can check the date and see, yeah, that's the one we did on such and such a date. And then I'll move those into archive. It gives me a chance to correct any errors. Sometimes, strange as it may seem, I make mistakes. And I do corrections there, and I get rid of dead air. Like if we take a break, say, then I let it keep running because in the past I've paused it and forgot to start it up again. So I don't do that anymore. It runs all the way through, and then I just cut out the dead space. Okay. Let's see. There are some supplemental documents. You can look at those if you want. This is solutions to end of chapter problems, but you probably won't need those because the homework uses those end of chapter problems, and they give you several opportunities to answer them correctly. And it's set up so that it'll give you hints. And if you just completely bomb it, then it'll come up and tell you this is the solution to it. So you really don't need that anymore. I can't remember how many opportunities do I give you to answer it? 10? Yeah. So by that time, you probably ought to have the thing memorized. Okay. So any questions? Questions? Great. You can stop me anytime and ask questions. Let's stop this share and take a quick look at the syllabus. There are a couple of things that are different even from the first semester, because this is in the summer and naturally we're stretched for time. So that's what the syllabus looks like, and all this is standard stuff. You're going to see it pretty much the same way for any course you take here. If you need to meet, I don't have office hours in the summer, but if you need to meet and we set up an appointment, you can either come face to face to my office. I left that out. No, I didn't. R129. It's just down the hall. But if you have a lot of travel, if you have to travel a long way and you still need to meet, we can Zoom a meeting. Now, I can Zoom it from here. I can Zoom it from home. That meeting ID, 295-716-1648, is my personal Zoom ID. So that's the one that you would go to have a Zoom meeting with me that's scheduled. When we schedule for a certain time, that's when I'll open up the Zoom meeting and you go in there. There's no, I should have put a link. I think I have a link later. I'll show you where you could just click it. You don't have to open up Zoom and then put in all that information. My personal Zoom meeting doesn't have a passcode. Right, so once, that might be crazy, but I just don't do it. Okay, you need to have had the first semester, of course. This is a face-to-face class, and these are the times when we meet. You already know that, I'm sure. These are the current prices for the Cengage textbook. If you're only going to be here for this one class, then buy the one semester. It'll last for 4 months, $162. But if you want a hard copy, right? I come from old school. We always had hard copies. These are the details for the 10th edition. You can use an earlier edition as long as you've got the homework, access to the homework. You can use an earlier edition, or you can use a used 10th edition, right? That's more reasonably priced. And those are the details. I just like the feel of paper. These are details about the course. Probably the more important one is this one right here, the grade average. All right, we got 54% are your chapter exams. I think there's 7 of them. So they're going to come quick. And then the final exam is worth about 2 chapter exams, 16%. Homework's worth 20%. Showing up and participating, 10%. And then, of course, your extra credits are, okay, I made those 10%. That's more than 2. Yeah. Okay, so you get a lot more credit than I thought for crosswords. But since it's in there in black and white, I can't change it. Not on the day of, right? If I had caught that before, I could have changed it, but I can't change it now. You need a calculator. Everybody got a scientific calculator. If you go to Walmart and buy one that says scientific on it, it'll have everything you need, because that's what you use for tests. You're welcome to use your phone calculators any other time, but on exams, only those scientific calculators, because smartphones are too smart. Let's see, course outlines. We will have regular exams, homework. Those are some details. Attendance, bonus or extra credit. The crossword puzzles are regular extra credit exercises. This semester, you won't need to do the extra credits like I had you fill in the periodic table, and that stuff. Or we had you name the naming compounds, because that's in the past. This semester, in this course, you have regular crosswords or extra credit, and then exams usually will have some bonus questions on them. And you get credit for those. If it's just a case of memorization, then you just select the answer, and that's good. But if there's any calculation required for extra credits, bonus questions, you have to show me your calculations. All right, so here's the schedule, and this is the same thing that I put in in Brightspace. I just took that table out and stuck it in Brightspace. Here's the invitation link for the course. So if you have to Zoom, just go in and maybe highlight it. I don't think it's set up to do a direct click. It might work. Let me see. Control. No, sorry. So it's just text. So just highlight it, copy it, paste it into your browser, and then you can join the meeting by Zoom. Now that works if we don't have a lab on that day. And on most days we will have labs because we only got 10 weeks.
No, we still get participation points if we go on Zoom.
If you're on Zoom, yeah. The one thing that's different with this course, because it's in the summer and we only have 10 weeks, is that in a regular semester, I like to have exams and labs not on a day we have exams. But I can't do that for this. We're going to have labs on exam days. All right, so we got to get those exams done. And if there's any lecture involved, we got to get them done quick so we can do the lecture too. So it's unavoidable. So this gives you, I highlighted the exam and homework due dates there. Let's see, we got how many? Yeah, I was right, 7. And then a final exam. And we do have time to do reviews. Yeah, it looks like I've got reviews for everything. I think we ran into a pinch last semester, didn't we? Let's see. Do we have any holidays? Independence Day, that's a Thursday. All right, so we won't meet labs or lecture on that day, July 4th. And if I got my dates right, then we should finish on time. There's one that there's no lab, but that lab comes later. So there's one day with no lab, and the first meeting is just discussions of the lab. But the rest of the Thursdays, it looks like we have labs. Okay. So that's stuff you can read on your own. This is how you connect with me outside of class. I was looking for the I was looking to see, there it is. All right, so there's an invitation. You don't have to open up a Zoom app. You just take that one right there and paste it into your browser and click on it and yeah, click on it. And it should open up the Zoom meeting. And that's only if we have pre-scheduled a private meeting. Otherwise, I won't be there. Okay, this is an appendix for how you deal with your homework, how you get registered, and examples of what it looks like when you get in there. Let's see. I think I set up the same deadlines in the OWL homework as you have in the syllabus. But there's a possibility that I missed the dates in the OWL homework don't jive with your syllabus. When there's the tiebreaker is the syllabus. The syllabus tells you the dates that everything is due. And if the homework comes up and tells you that it's due a week from now, or it was due yesterday, don't believe it. Believe the syllabus. And just tell me so I can fix it. Okay, good deal. Let's see. We're only going to discuss this if you have to take an exam online. I prefer, since we only have 10 weeks, I prefer you show up for every exam because we're going to have activities after it anyway. So this option for taking exam online is probably not valid.
Next Tuesday, after we leave for the first exam, I still can take that exam.
Leave for a vacation. Are you going to Zoom while you're out of town?
Absolutely.
Okay.
I was wondering about that because if I go ahead and take that exam on here, I could Zoom for the lab.
Zoom for the lab. No, we don't Zoom labs.
Mhm.
Now, sometime, if we have a discussion about the lab, I'll Zoom that part. That'll be recorded. But the activities in that yeah. Yeah,
First couple hours.
Maybe I misunderstand your question.
Yeah, the last semester was, I think the first or second of it was, we didn't go in the lab. Like,
Oh, no, it's all hands-on this semester. Yeah. There are a couple that are informal reports. Huh? Well, they're in the syllabus. I identified them in the syllabus.
the first two I've seen.
No, the first one and the last one, I think. No, not the first one. Le Chatelier's principle. So that one's on June 13th. Le Chatelier is an informal report. You do the exercises and you fill out the hard copy and turn it in. That's an informal report. And then the last one, electrochemistry, that's an informal report too. But the others are formal reports, and we'll talk about that on Thursday, how to do a formal report.
I was on the 30th. On this.
Okay.
Work is a review that happened, but using that.
Okay. And let's see.
After everything's done, better chemist. You can just. Didn't go to text. Use it.
Oh, okay. Yeah, after everybody in here gets finished with the exam, then you can Zoom in. Okay. Okay. And then, well, you pick your partners on Thursday. We'll talk about that later. So that you know who to contact if you're missing information. Okay, any questions? I think that was the end of it back down here. Well, there's a Zoom attendance of the class, right? Details. Just to be thorough. That's why my syllabi are always thick. Because I have everything that you would ever want to know about the courses in there. Okay. So let's see. I got an hour and a half to cover chapter 10. I think we can do it. So where did we leave off last semester? Can't remember what the last topic was. Can you? Chapter 9. Oh, I know. Bonding. Right. We had 2 chapters that both talked about bonding. We ended up with molecular orbital theory. Right. Now we're going to, and the first semester we do sort of skim across the top of liquid solids and gases. Now we're going to dive deep. and talk about, actually, we're going to talk about both covalently bonded molecules and ionic compounds, both. But this intramolecular bonding, this happens within the molecule. So we're talking, when we say molecule, we mean covalently bound. Right? That's the definition of a molecule, because it acts as a single unit. Whereas ionic compounds, you just have an array of positives and negatives, cations and anions. Okay. So when we say molecule, always think covalently bound, like water molecule. Right? They're independent; they float around, and the bonds that hold them together, right? Those are the intramolecular bonds right here. Okay, they have a certain strength, and we know how to determine that. Right? We can make a gas out of it and then put enough energy into it to break the bond, and we can measure it. So we know how strong these bonds are. But there are forces that are between molecules. And we've determined that the water molecule is polar, right? It has polar bonds, correct? Like that. Plus it has two lone pairs up here. So it's very polar in that direction. Okay, it has a negative side and a positive side. Well, as an individual molecule, the negative part is up here, and the positive parts are down here. So if it encounters another water molecule, like say one's down here, this is going to be, negative. So there's an attraction between those two. It's electrostatic. Right? It's not a full charge. Right? We know that. But it's strong enough to affect the physical behavior of water or whatever molecule we pick. If it has those forces are available. These are intermolecular forces. Between molecules, within molecules. Okay, and they come in several flavors. If you have a dipole, that's what we call this. That's a dipole. If we have a dipole in one molecule, and let's just keep it simple, it's a pure substance. Right? We have pure water. This has a dipole, that has a dipole, and this positive dipole forms an attraction with that negative dipole. So that's a dipole-dipole force that's attracting them. Okay. Now, water has a special kind. Several molecules have a special kind of dipole-dipole, and it's called hydrogen bonding. It only happens when you have in the molecule somewhere, you have oxygen and then hydrogen. Or you have, let's see, nitrogen, that works also, on some part of the molecule, or you have fluorine. And that's all it would be. Because fluorine can only have one bond. All right, so these will give you the strength, the electronegativity relative to hydrogen for each one of these elements is strong enough that it forms an extremely strong dipole. That direction. That means that the electrostatic attraction set up here is the strongest there is of the dipole-dipoles. It has everything to do with electronegativity. And not just that, but the size. Right? These are all second periods. Right? They're small enough, which means that they form the dipole, but they don't get in the way. There's no steric interference. They're small. And hydrogen, of course, it's just a proton. Right? So they can get close to each other. And that adds to the strength of the dipole interaction, the hydrogen bond. Okay. Now, we talked about two types of forces involved here, intermolecular and intramolecular. Which one's stronger? It's not a trick question.
Internal.
Yeah, the intramolecular has to be stronger. Why? Because if this were stronger than that, it just rip the molecule apart. Okay, and it's simple logic, actually. So we know that going in, that these bonds have to be stronger than those bonds. And there's an artist's idea of what water looks like. Of course, if it's a liquid, these interactions are fleeting, they're temporary, right? We'll have an attraction for a while, and then it'll vibrate and it'll break loose of that one and go find somebody else. Only when it's in a solid form will these attractive forces be more or less continuous between two individual molecules. And if we form ice with water, what we tend to do is the water tends to set itself up in a hexagonal shape. So you would have maybe an oxygen here and a hydrogen here, and then another hydrogen there. And then we would have, let's see. This would be an oxygen. Yep, that works. So it sets itself up in a hexagon. That's why snowflakes have 6 points, because of this internal structure of ice. I digress. Let's move on. Okay, we already answered that question, and there's my explanation. Okay, these intermolecular forces experienced between molecules determines physical characteristics of the substance. And we'll look at several of those. One is phase changes. When the substance goes from solid, liquid to gas, those intermolecular forces, the strength of those forces determine what temperature the phase change will occur. Now, if oxygen, the dihydride of oxygen is water, and then you have sulfur, hydrogen sulfide, H2S, is analogous to oxygen because it's in the same group. And then you can have selenium, hydrogen selenide, and you can have tellurium selenide, hydrogen telluride. Right, and if you look at each one of those and their melting points or boiling points, either one works. What happens is the temperature decreases. Actually, the temperature increases as you go down, the boiling point or the freezing point. So it takes more energy as you go down. And that's the trend is for this one, and this one. But oxygen doesn't behave. In fact, I think I've got a graph for that. Oxygen dihydride doesn't behave the same way because of that hydrogen bonding effect. If it weren't for that, then water would, on the surface of the earth, would be solid, I think. Hold on a second. I digress again. Let me get back on track here. These are representations of different phases. You notice that the individual molecules for a solid are in a regular array, right? That's so they can hold their shape, they can hold their volume without any containers. Liquid, on the other hand, has a regular volume, a constant volume, but it doesn't have a constant shape. It needs a container. And then gases, they take the volume and the shape of their container. And it's largely due to the fact that, notice that the gas molecules are moving really fast and they're very far apart. There's lots of space in there. So when you go from a solid to a liquid, you have to add energy. Like you melt ice, you have to add energy. If you hold the ice in your hand, it's going to feel cold because it's taking energy from your hand to melt. And that energy is absorbed to overcome part of the intermolecular attractions. So think about it this way. Any substance that phase changes from a solid to a liquid requires some energy input. It's endothermic. Some energy input to overcome those attractive forces. So if you know something about the attractive forces, whether it's absolute amount or relative to some other substance, you can say things about when it phase changes. If you know an absolute value, you can say this is the temperature, or if you know just a relative attractive forces, then you can say one melts at a higher temperature than the other one. Same thing for liquids and gases. Now, when you go from a solid to a liquid, it takes a certain amount of energy. When you go from a liquid to a gas, it takes a lot more energy. You're completely breaking those intermolecular bonds. Those gas molecules are essentially free from each other. If they do encounter one another, the attractive forces are usually overcome by the kinetic energy that they have during the impact. Now, we talked about water before. Going from a solid to a liquid occurs at 0 degrees Celsius in 1 atmosphere. Going from a liquid to a gas, okay, those temperatures are not accurate. Going from a liquid to a gas is 100 degrees Celsius. But these densities were measured at different temperatures. That's why they put those in there. The point is, normally when you go from a liquid to a solid in any substance, the density of the liquid compared to the density of the solid should be greater normally, because the molecules are getting just a little bit closer together to fit into that regular array. But water's different. And I showed you why it was different. Because when it goes from a liquid to a solid, it organizes itself in those hexagons and introduces empty space. So that empty space decreases the density. So water's different. And it's a good thing it is, actually. Because if it wasn't, one winter, the oceans would get a layer of ice on top, and it'd be more dense than water, so the ice would sink to the bottom. And you just keep freezing until, it may take several winters, but eventually the ocean would be solid ice from top to bottom. So the fact that ice floats is a good thing. It's less dense than liquid water. Okay. When I drew that arrow to show you the dipole like that, that's referred to as a dipole moment. This terminology is derived from physics. A moment is a force in a particular direction. It's a vector. Have you ever heard the term vector used? Yeah. A vector is a size. It could be a force, or it could be something else, but it's in a direction. If you just have a perfect example, speed. You're tooling down the highway at 70 miles an hour, right? You go around a curve, you're still doing 70 miles an hour because you're going to put a little more energy into it, right? So you don't slow down going into a curve. Your speed stays the same, but your velocity changed because you were going this way at 70. Now you're going that way at 70. That's a change in velocity when you change direction. That's a vector property. And dipole moments are vector properties. So the molecule will have a particular vector in a certain direction. Water, of course, is like this. It's vectored that way. Other molecules might be vectored in different directions. Or you might have a molecule that's long enough that this part of the molecule has no dipole at all. And on the very end, you've got, say, oxygen and hydrogen. So it's got a dipole on the very end. So those bigger molecules have the opportunity to be both polar on one end, nonpolar on the other. That's why soaps work. Soap is an example. That's why you can get grease out of your clothes using soap or detergent, because one end is nonpolar and dissolves in the oils, and the other end is polar and is hydrated by the water that's in the washing machine, right? And it picks that oil. Most soils in your clothes are oil related, so it picks that up, flushes it out, and throw your clothes in the dryer. I don't know. Does anybody hang them on the line anymore? You do? Okay. Is that by choice?
Yeah, sometimes,
Okay.
just not in the spring.
Uh,
Probably.
Oh, plowing, yeah.
And not in the winter because it freezes.
Okay. Okay. So these molecules with dipoles can attract one another. We've talked about that already. And the dipole, the strength of the dipole interaction is only on average about 1%, the strength of a covalent or ionic bond. Okay, so it's a lot weaker, and that's a good thing. All right, we talked about the hydrogen bonding, and it's characteristic of hydrogen bonded to either nitrogen, oxygen, or fluorine. An example of nitrogen would be right, ammonia in H3. It would have a dipole that direction. So you'd have positive here and negative on this side. Oops. And liquid ammonia, 100% anhydrous liquid ammonia is actually, well, I already said it, it's a liquid at room temperature because of that. Now, it's very volatile. It's more volatile than water, right? The dipole isn't as strong as it is with oxygen, but it still keeps it in liquid form as long as you have the container sealed. You don't have to cool it to keep it down there. So farmers use that, right? It's a cheap way to add nitrogen to your crops. You just set up your tractor, get a big tank of ammonia back there, and then you run it through pumps, and it's all stainless steel, it has to be. You run it into your injectors that sit below ground. So you inject it into the ground where there's moisture, and the moisture combines with the ammonia to create ammonium hydroxide. And that won't volatilize. So that's the only way. I mean, if you just sprayed it on the ground, it'd be liquid for a few seconds and then it's gone. So they inject it into the ground. And the first thing that happens is you get the pH run so high that you create a kill zone like that around the injection. So you don't want to inject it right next to your plant roots. You want to do it in the middle of the row. And then eventually microorganisms reinvade and use the nitrogen, and the plants can send their roots in safely, and you get your nitrogen. It's good for corn, sugarcane, all the grasses. They're very heavy nitrogen users. Okay, I digress again. All right, so we talked about dipole-dipole interactions as one possible intermolecular force. I'm going to introduce one that's not in the slides. At least I haven't seen it yet. It may be in there. But if you have something like water and you put table salt in it, okay, the salt's going to split apart into its sodium ions and fluoride ions. In that case, those ions will be hydrated by water and you have a dipole ion interaction. And we're still electrostatic, right? Positive attracts negatives. But if you have molecules, if you have a substance, a pure substance that's nonpolar, let's see, what would be a good example of a nonpolar substance? How about octane? Right, the stuff you burn in your gas tank through your engine. Octane has 8 carbons and let's see, 18 hydrogens. So there's your octane. Well, at room temperature, it's a liquid. Why is that? Right? There's no dipole to hold the molecules together. So what holds them together? It's called London dispersion forces. You got this long molecule, say 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons. There's a carbon at each one of these intersections. And then, of course, you have 3 hydrogens on this end because carbon has 4 bonds. And 2 hydrogens each here for 4 bonds, right? 2, 2, 2, 2, 2, and a carbon with 3 hydrogens. So what happens is that electrons are always on the move. And occasionally, for just an instant, even quicker than a snap of my fingers, you get an uneven distribution of electron density in that molecule. So this end might, for a moment, become slightly positive, and this end might become slightly negative. And any neighboring molecule would sense that difference as positive, would attract electrons, attract electrons on this molecule toward that end and make it negative. And these would repel electrons on that end and make this positive. And there you have, or anywhere along that molecule that you have a difference, just for an instant, right? This is temporary, right? Dipoles are permanent. They're part of the molecular structure. But London dispersion forces are temporary. But they are strong enough to increase the boiling point of octane to the point where it'll stay a liquid in your gas tank. Now, another example is nitrogen. Right? Dinitrogen, the stuff we breathe. Right? That's definitely nonpolar, right? Because they're both the same element, right? But it doesn't stay a gas as you get colder and colder and colder. It actually turns to a liquid when you get down to minus 195 degrees C. So how does it do that? Same way. London dispersion forces. Now, one thing about the London dispersion forces is they're always there. Every molecule, whether it's polar, nonpolar, doesn't matter. London dispersion forces are always there. Whether they're significant to these physical properties is the question. Now, if you've got dipoles in your molecule, then the London dispersion forces are so weak, they don't matter. you can ignore them. But if you have a nonpolar molecule, then the dispersion forces become significant. And they contribute to these values that we see in nonpolar molecules. All right. So how are these physical measurements that we can make, how are they related to the forces? The stronger the intermolecular forces, the higher the melting point, the higher the boiling point. So if the forces, as they get stronger and stronger and stronger, it takes more energy to break those bonds. So the temperature required to break those bonds goes up. Melting point, boiling point goes up as the strength of those intermolecular forces increases. Here's the one I was looking for before. Okay. Let's focus on the top one, the one with water. If we followed the trend and we went from period 5 to 4 to 3 of the dihydrides of those elements in that group, then what you notice is as you go from in this case, from the bottom to the top, the boiling point is decreasing, right? If we followed the trend from there, then water should boil at about minus 80 degrees Celsius. But it doesn't. It boils at 100 degrees Celsius. And the explanation for that is hydrogen bonding. Sulfur, selenium, tellurium, electronegativities are not great enough to establish a significant dipole with their hydrogens, right? You will have some, but it's not the same strength that the hydrogen bond is. So water breaks with the trend here. And actually, hydrogen fluoride breaks with its trend of the halogens, and nitrogen breaks with its trend for the pnictogens. But when we get to the carbon group, everything falls into line. You go, let's see, if this is methane, this is silane, this is germanium. I don't know how to say that one. And then 10, stanane. I don't know. Anyway, the trend is what we would expect. Okay. But when you've got nitrogen, hydrogen, nitrogen, fluorine, or oxygen involved with hydrogen, you get that hydrogen bond introduced. And that is the fly in the ointment. Okay, which molecule capable of forming stronger intermolecular forces? Well, obviously water is because it has hydrogen bonding available. Nitrogen only has London dispersion forces. Right, and there's your explanation. Okay. If you got, all right, I didn't add the London dispersion. The key to this one is that dispersion. London's the name of the guy who proposed it. Dispersion is what's actually happening. You disperse your electrons unevenly in the molecule. Now, with this slide, we're drawing a distinction between, we have a molecular formula like that, but it can be drawn as two different isomers. That's what we call these are structural isomers or conformational isomers. They got the same formula, but the atoms are connected differently. So if they're connected, if the two carbons are connected together, and then we have hydrogens on this side, and then this is connected to an oxygen and it's got a hydrogen on it. Let's see, two more hydrogens. 3, 6, there we go. This is ethanol. This is ethyl alcohol, you know, the drinking kind. And it has a certain boiling point. Okay. But if we rearrange those and actually put the oxygen in the middle, hydrogens are here. That changes everything because this is a site for hydrogen bonding. Whereas this one is symmetrical. And even though the dipoles on the bonds are this way, they cancel one another. This is dimethyl ether. And its boiling point is much, much lower than that one is. This one's about 78 degrees Celsius. I don't remember what this one is, but it's really low. It's like negative 30 or 40. And that simple change in structure changes the boiling point. Okay, which one of these would behave more ideally at the same conditions of pressure and temperature? Remember when we talked about gases and ideal behavior, what are the conditions for ideal behavior of a gas? High temperature? No? Right. High temperature and what? Low pressure? Any gas will behave ideally under those conditions. Now, what do we mean by ideal behavior? Remember that? What is ideal behavior? Okay. An ideal behavior for a gas is it's always a gas forever, no matter what you do to it. Right? You cool it down all the way down to absolute zero if you could ever get there, and it stays a gas. Stays a gas at any temperature. And you could add pressure to that too, temperature and pressure. And you can increase the pressure, decrease the temperature, and it would still be a gas. So what would affect a gas relative to ideal behavior? The one that has the weakest forces that have to be overcome, right? Because high temperatures overcome those intermolecular forces. Low pressure means that there are fewer gas molecules in there to interact, so you don't have frequent encounters. So the way to predict ideal behavior or more ideal behavior for one gas over another one is, first of all, is the gas polar? So if we draw carbon monoxide, right, it's polar this way. Not much, but slightly polar. How about nitrogen? Well, we know that one already. It's nonpolar. That means the only forces available to this one are London dispersion forces, which are extremely weak. But this one has dipole-dipole interactions, which are a lot stronger, which would make it behave non-ideally. Okay? So we should pick the more ideal one would be nitrogen. And there's your explanation. Okay, I'll leave that up there for now. Okay. We looked at solids temporarily. We'll come back to them in a few minutes. Liquids. Characteristic of liquids. They have, like solids, they have very low compressibility. Actually, solids are essentially no compressibility. Liquids do have some compressibility because there's a little bit of space that's between them, which allows them to slide past one another, the molecules. So if we reduce that space, then we can compress them. Under pressure, they will compress some. And we know that's true. There was a time when we thought water, or the liquid water, was incompressible. But measurements have been made of water at 2 miles down the ocean. And it's more dense. And not just from salinity either. It's dense because the water molecules are pushed closer together. So liquids are very slightly compressible. They're not rigid. They can't hold their own shape. They have relatively high density as compared to gases. They exhibit this phenomenon, and it varies depending on the liquid, called surface tension. Surface tension is defined as the resistance of a liquid to an increase in its area. In other words, when you can tell the difference in surface tension of a liquid by having a clean table, absolutely clean, and then take your various liquids and just put a drop of each one on the table. The one with the highest surface tension will bulge up into a ball on the surface. And the one with the lowest surface tension will go and just spread out. Okay. That's an example of comparison of surface tension. Water tends to have a reasonably high surface tension. And there are some insects that take advantage of that. You've seen water skimmers. You have to watch them on calm water. Right? If it's turbulent, then all bets are off. But if it's calm water, you can see these insects with their legs sticking out. They've got 6 insects, of course. They have 6 walking legs, and they're spread way out with toes on the end of them. And wherever they touch the water, there's a depression in the water, but the insect doesn't sink below the surface. They're using that surface tension, that force of surface tension, to support their weight. Now, the high surface tension is characteristic of those molecules that have larger intermolecular forces holding them together. Let's see. Another characteristic of liquids we can identify as capillary action. The capillary action is, you know what a capillary is, right? It's a very narrow tube. So I'm going to draw it. I'm going to expand it. Okay. That's our narrow tube. And we've got a liquid in here. Well, if there were no capillary action, where would the liquid be? It'd be right here, wouldn't it? Right? But depending on what that tube is made of, and let's use water and glass for an example. Right? This is water, and this is glass. So what's glass made of predominantly? Silicon dioxide, right? Sand, and plus a bunch of other stuff. But it has lots of oxygens on its surface, right? Lots of oxygens. And oxygen is electronegative, so they're going to be slightly negative, right? All those oxygens on the surface. So what's happening is this water being polar, the positive side of water is attracted to these guys right here, and it climbs up the sides. Right? It goes up like that. Okay. Think of this in 2 stages. It's attracted to the walls of the capillary, and then the molecules that are in this part that's pulled up are attracted to each other, and they pull the rest of the water up with them until there's a balance. Right? And then we do it again until we reach another balance. And then we do it again until we reach another balance. We only go as high in the capillary as the forces of attraction will support the mass, that mass right there. So the narrower the tube, the higher it'll climb, right? Because what's the volume of a cylinder? Like height times area. So if we decrease the area, we can go higher. If you have a tube like a regular, if you had a glass straw, say McDonald's they had a marketing campaign and they were using glass straws. If you had a glass straw, you wouldn't see any movement of the liquid. because as soon as it tried to move up, it would exceed the mass that it could support. But if you use the capillary, that's another thing. Let's see. I'm not sure if any of you have ever used capillaries in your line of work. These little tubes are about that long, they're very narrow, and they were used to take samples. You take a blood sample, and then you dip your capillary in the blood sample, and it fills up to the mark, and then you put it in your centrifuge and spin it. And then you stick it in a thing and read it, and it gives you the hematocrit, right? What's the percentage of red blood cells versus plasma? Okay, so that's one way to use capillaries. Okay, so think of it also as a battle between cohesive forces and adhesive forces. The cohesive forces are the ones in here. Cohesive forces holding the molecules of water together. And the adhesive forces are the ones here, between the water and the walls of the capillary. So there's a battle going on. And when we get the total forces of adhesion equal to the total forces of cohesion, then it stops moving. Now, this is for water. If we do the same thing with mercury, like mercury, what we find is mercury just sits right here. It doesn't move because its cohesive forces are orders of magnitude stronger than the adhesive forces. It has virtually no attraction to the glass tubing. So that's why when you have mercury in a device, what you see there is not a concave meniscus, but a convex meniscus. And if you've ever seen a mercury barometer, or if you go into a doctor's office and they've got a sphygmomanometer on the wall that use mercury, they don't use them anymore. They just keep them up there for show. And you see the scale, you see the mercury in there. It's got that convex meniscus in it. Or if you see a barometer, there's one in the chemistry lab on the Greenburn campus, hanging on the wall there, and it's a mercury barometer, and it's a little bit different because up here, let's see, up here, that's a vacuum. So what's supporting it is air pressure is pushing here, and it goes up a certain height. But it still has that convex meniscus because of the balance between the cohesive forces and the adhesive forces. Cohesive is stronger for mercury than the adhesive forces. Whereas water, the other way around, the adhesive forces are stronger than the cohesive forces. And that's why they pull up the walls. And then the only thing that stops them from moving is mass. Okay, another characteristic of liquids, viscosity. Got an idea of what viscosity is? Viscosity is the resistance of a liquid to movement, to flowing. Think of molasses in winter, right? You have a jar of molasses, you sit it outside for a couple hours, and then you go out and you take the jar and you go like that. Nothing happens. The colder it gets, the more viscous it gets. And if you heat it up, it flows better. The viscosity goes down. So, and that also depends not just on temperature, but on the forces between the molecules. If the forces are stronger between the molecules at any given temperature, the forces are stronger for this substance than it is for this substance, then the stronger forces will increase the viscosity. right? Large intermolecular forces contribute to high viscosity. And there are several ways that you can measure it, depending on what industry you're working in and what the substance is. Is the substance really thin, or is the substance relatively thick? You can, I've seen various tests you can use. You have this board, and you put a certain amount of your liquid right here, and then you have a scraper, and you scrape it, and you measure how far it goes before it runs out. Or you have a device with a hole in it, and you put a measured amount in the top, and you count the time it takes for all of it to run through that hole. And the faster it runs, the less viscous it is, and they're calibrated. Or if it's really thick, you can use a penetrometer. So you can have your liquid here, and you can drop this pointed device, and it goes, and it has markings on the side, and you see how deep does it go. And all of these are calibrated to a certain measure of viscosity. I mean, we're not going to do any calculations. This is just a theoretical discussion. Okay, let's talk about solids now. We have we divide a discussion of solids into roughly two categories. One is crystalline solids. A crystalline solid is just what you might think. It's a translucent or a transparent solid that looks like a crystal. Everybody has an idea of what a crystal is. Salt is a good example. Table salt, right? I've mentioned this before. Spill some on the table and look at it with a magnifying glass. What do you see? These little cubes, right? It's a crystalline solid, and that is an indicator of how the sodium and chloride ions are arranged. They're very ordered. And because they're ordered, and because the size of the cube is only dependent on how many of each of those are in the group, we can reduce it to what we call a unit cell. In other words, we can identify a repeatable unit in the crystalline solid. And we're going to talk about unit cells in a little bit. And then there are amorphous solids. Those that are definitely solid. I mean, they meet all the qualifications for being a solid, but there's no ordered structure to them. Glass is a good example. Glass is an amorphous solid. Okay. This unit cell I mentioned just a second ago is the smallest three-dimensional repeating unit in a crystal. So if you can identify the unit cell, then all you have to do is just stack as many of them as you want together in a regular array, and that will produce the size of solid that you desire. Now let's see, the second description. These are two different ways of describing the same phenomenon. Remember, I've always said nature just does what it does, and we try to explain it. Unit cell is one way to explain crystalline solids, and closest packing is another way to explain it. And they do meet occasionally. So if you know one, you can predict the other. Not always, but there's some relationship. There's kind of a Venn overlap. Some unit cell works for some types of discussions and calculations. Closest packing works for other types. We're going to look at each one. Now, the unit cell comes in multiple flavors, but most crystalline solids can be described by one of these three unit cells. The simple cubic is simply that, right? We've got a cube right there. And at the corner of every cube is an atom or a molecule. We're going to keep this simple. right? We're just going to say they're atoms for now. But you can do this with molecules also. So how many do we have there? Looks like 8, right? Okay. And then that's the simple cubic. Then you have the body-centered cubic, that BCC. In this case, you've got, in our example, an atom at every corner, plus you've got one in the middle, body-centered. Okay? Now, these are 3 different ways of representing them. What do they call that? The ball and stick model is at the top for the single unit. And then below it, it shows that in a lattice arrangement, you know, with other unit cells. And then below is actually what happens, is the space filling unit cell. Problem with space filling is sometimes it's hard to see what the rest of the structure looks like. Then you have a face-centered cubic. And a face-centered cubic still has every corner occupied by an atom. But at every face, 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3, 4, 5, 6. Yeah. You'll have an atom at every face. So that's on top. This is on the side. This is on that side. This is on the near side. And then this is on the bottom. 1, 2, 3, 4, 5, 6. So every face has a portion of an atom attached to it for that unit cell. Let's see. Oh, there's a discussion coming up. What I want to call your attention to is with this one, I drew these just as balls and sticks. But when you look at the space filling model, they're big enough to where they actually touch along the perimeters here. Okay. But when you stick one in the middle, that pushes these guys apart, so they no longer touch. And then even further, if you put face-centered in there, that keeps the corners from touching. Now we're going to talk about, in a few minutes, we're going to talk about identifying how many atoms or how many molecules are associated with each unit cell. Right. This shows a unit cell with 8, but they also share them with other unit cells. So really, only part of that one belongs to that cell. So that's where we're headed. But I've got I think a video coming up.
If you could travel within a crystalline solid, you would see the particles, atoms, ions, or molecules arranged in a regular array. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. The unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all 3 directions gives the structure. Many elements and simple compounds have unit cells from the cubic crystal system. Let's examine the 3 types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges, but not along a diagonal in the face or along a diagonal through the body. By slicing away parts that belong to neighboring unit cells, we see that the actual unit cell consists of portions of the particles. When the cells pack next to each other in all 3 dimensions, we obtain the crystal. If we fade the others out, you can see the original group of 8 particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles' portions. In the simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combine to give one particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, any given particle has a neighboring particle above, below, to the right, to the left, in front, and in back of it for a total of 6 nearest neighbors. The body-centered cubic unit cell has a particle at each corner and one in the center, which is colored pink to make it easier to see. With full-size spheres, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center. The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8 give one particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any given particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. The face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. The corner particles don't touch each other, but each corner does touch a particle in the face, and those in the faces touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8 at the corners gives 1 particle, and half a particle in each of 6 faces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 nearest neighbors around it, 4 more above and 4 more below for a total of 12 nearest neighbors. Stacking spheres shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical rows. Note the large diamond-shaped space among the particles. Placing the next layer directly over the first gives a structure based on the simple cubic unit cell. Those larger spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres. Because of this inefficiency, the simple cubic unit cell is seen rarely in nature. A more efficient stacking occurs if we place the second layer over the spaces formed by the first layer, and the third layer over the spaces formed by the second. That simple change leads to 68% of the available volume occupied by the spheres and a structure based on the body-centered cubic unit cell. Many metals, including all the alkali metals, adopt this arrangement. For the most efficient stacking, shift every other row in the first layer so the large diamond-shaped spaces become smaller triangular spaces, and place the second layer over them. Then the third layer goes over the holes visible through the first and second layers. In this arrangement, called cubic closest packing, spheres occupy 74% of the volume. Note that it is based on the face-centered cubic unit cell. Many elements, covalent compounds, and, as you'll see in the next 2 examples, ionic compounds adopt cubic closest packing. Sodium chloride adopts the sodium chloride or rock salt structure, as do many other alkali, halides, alkaline earth oxides and sulfides, and other ionic compounds. Picture separate face-centered cubic arrays of chloride ions and sodium ions as they approach and interpenetrate each other. The smaller sodium ions fit in the holes between the larger chloride ions and the NaCl unit cell. Zinc sulfide adopts the zinc blend structure, as do the copper-1 halides and several other compounds. If face-centered cubic arrays of zinc ions and sulfide ions approach and interpenetrate slightly offset from each other, each ion becomes surrounded tetrahedrally by 4 of the other ions. Note the blinking zinc ion and the 4 sulfides. You can see the relative positions in this slightly expanded view of the zinc blend unit cell.
And that looks like it's also, at least for the sulfides, it's the face-centered cube. All right. So what we got from that discussion was each one of these cells for the simple cubic is represented by one atom. And for the body-centered, it's 2 atoms. And for the face-centered, it's 4 atoms per cell. And the coordination number simply means if you focus on any one of these atoms, how many does it have closest neighbors? There's 6 for this one, 8 for that one, 12 for that one. All right. So the question is, how do they know this stuff? How do they know the spacing of the atoms? Well, as it turns out, there was a man and his son. Of course, both their last names are Bragg, so that makes it easy to name the equation after either one. The Bragg equation, which is a number times a wavelength that's of the light that shined at the crystal. And then D is the distance between the layers. And theta is the angle of reflection. It's the angle of maximum energy. So let's see. These are usually X-rays. And we need very short wavelengths because the distance between the atoms is very small. And we're using a phenomenon called diffraction. So we're treating light as a wave. And this is what it looks like in sketched out. So we have those black dots represent the atoms that are in one layer and the black dots below it in another layer. And if we shine X-rays at them, one wavelength might bounce off the top and the next one bounce off the second layer. And you can measure the strength. You can get a trace of the light based on the angle. So if you fire the X-rays at your surface, and you have a device out here, I'm going to represent with an eye, and you fire your X-rays here, and you move your eye backwards and forwards, you can measure based upon that angle. You can measure the strength of the reflection, and you can get a peak. So for this given wavelength here, you would have a trace, and this would be in the intensity of reflection, and then this would be the angle. So if you're at a certain angle, it might go along like that, maybe like that, and then all of a sudden, like that. And that angle would correspond to constructive interference. In other words, where the light beam striking the surface and the light beam striking the next layer are in synchronized. So the hills match the hills on each one, the valleys match the valleys, and they constructively interfere. And that gives you this strong signal. And that tells you, using the Bragg equation, that tells you what's the distance between those layers. I use this on soils. Wanted to find out what kind of clay was part of my soil that I was investigating. So I went through a whole week-long procedure of separating the particle sizes, the physical sifting first, and you get down to a certain small size, and then you suspend that in water with a phosphate buffer that breaks the adhesion between the particles. And then after you mix them up, you let it settle, and using another equation, you find out that if you go down with your dipper and you sample at a certain depth, you're only going to get clay particles at that depth. So I suck those up, and then I put them on a slide, let them dry. And as they dry, clay particles are like little plates. And as they dry, they just flatten out like that. So then you stick it in the machine and you do this scan. And I found out based upon that angle of reflection and the distance between the layers, what type of clay I was dealing with in that soil. Okay, now that's just for 2 dimensions. You can also use X-ray diffraction in 3 dimensions. And it gives you a pattern. So if we put that crystal in the beam, and the light that shines through the crystal is diffracted a certain way, and it gives you this pattern, then with experience and other samples that you know their structure, that have been determined their structure, then you can deduce what is the structure of the crystal. This method was used to determine that DNA was a double helix. Now, the trick with doing it with DNA is not typically a crystalline solid. So the difficulty was getting it into that crystalline arrangement so that this would work. And that was done, I can't remember her name. It was done by a woman, a researcher that worked with Watson and Crick. And she did all the legwork. And they got the credit. She didn't live very long though after that. After she did all that work, she died of some cancer, I think.
I remember talking about her in my biology class because we was talking about
DNA.
not the DNA. We was talking about DNA, but we was talking about the other guys.
Watson and Crick, yeah.
Yeah.
Yeah. I don't know if I put her in here. No, I didn't. Must be in a different lecture. Okay. So their crystalline solids can also be broken down into, see, we had amorphous and crystalline. We can take crystalline solids and we can form a crystalline solid out of ions. So sodium chloride would be an example. You've got cations and anions in that crystal structure. You can have molecular solids like ice, right, where you have individual molecules that occupy positions of a unit cell. And then you have atomic solids, which are the easiest ones to understand because there's just one atom in the position. If it's a simple cubic, they'll be at the corners. If it's a body centered, there'll be one in the middle. If it's face centered, there'll be a half of one on each face. Those atomic solids are just individual atoms. And most of the metals fit into that category. Okay, these are examples. Let's see. Different types of forces hold these things together. Right? With this particular one, diamond, all the forces in a diamond are covalent. In other words, every carbon atom is bound to 4 other carbon atoms with a covalent bond. What that actually says, if your diamond has no flaws in it, right? If it's perfect, flawless diamond, then you're actually looking at a single molecule, right? Because they're all covalently bound. That diamond is one molecule. My wife's engagement ring doesn't fit that because there's a flaw in it that we hid under the post. So you couldn't see it. The next one is sodium chloride. That's an ionic solid. And then you have a molecular solid, which I believe this is water. Yeah, well, there's the diamond. It's a network atomic solid. And let's see, metallic solids. Okay, the bonding that occurs between metals is, we've talked about ionic bonding and covalent bonding. There's one special to metals. And it's difficult to describe unless we consider molecular orbital theory. Because metals have relatively low energy valence electrons, so they can move among metals, among their neighbors very easily. That's why they conduct electricity very easily, conduct heat very easily, because those highest level electrons can, just a tiny amount of energy will kick them out, and they'll go find another atom. So what the author of your text has decided to call those is delocalized covalent bonding. I guess that's as good as any. Then we have, what are the 8A atoms? Noble gases. The 8A atoms, when we can form a solid from them, which is difficult, but when you form a solid, they are held together by London dispersion forces. And the larger the atom, the stronger the London dispersion forces. So the boiling point is going to increase as you go down, as the atom gets bigger. And the reason for that is the dispersion has more room, right? It's a bigger atom. The probability of finding more electrons over here and fewer over here is much higher with a larger body. So the larger atom will give you stronger London dispersion forces. So the boiling point increases as you go down. And you can say that about nonpolar molecules too, right? If we looked at we looked at octane earlier. That's part of an alkane series, right? Methane, ethane, propane, butane, pentane, hexane. As you get more and more and more carbons, you get a longer chain. And the longer the chain, the higher the boiling point. So you get to the point where you get into the diesel size molecules, and then you keep going, you get into asphalt size. The asphalt size molecules are huge, and that's what we use to hold the aggregate together on our roads. Okay, molecular solids. They're held together by dipoles or London dispersion forces. Could be either one. And then the ionic solids are the easiest ones to understand. They're just purely electrostatic attractions. All right, this closest packing model. I think the author identified the closest packing as giving you a face-centered cubic unit cell. That's the connection between those two. And in order to make the closest packing model work, we have some assumptions that have to be made. One is that all the atoms in this, and we're going to focus on metals, all the atoms are considered to be uniform hard spheres. Right? And these spheres are packed in layers. All right. This video coming up, I'm going to run over on that. So if you have to go, go ahead, and I'll finish the lecture and you can watch it on recording. The woman that narrates this has an Indian accent, not a Native American. I mean, I'm talking about subcontinent India. So once you tune your ears to her accent, then it'll make sense.
The three-dimensional modes of packing can be easily understood by dividing the whole process into 3 steps. Close packing of spheres in one dimension. In one-dimension close packing, there is just one way of arranging the spheres. Here, the spheres are arranged in a row, touching one another. As a result, each sphere is in contact with 2 neighboring spheres. Thus, in one-dimensional close packing, the coordination number is 2. Close packing of spheres in 2 dimension. Close packing structures in 2 dimension can be generated by stacking rows of one-dimensionally closed packed spheres, one above the other. This can be done in 2 ways. square close packing, and hexagonal close packing. Square close packing. In this type of packing, the second row of spheres is placed in contact with first row in such a way that the spheres of the second row are placed exactly above the spheres of first row. In such an arrangement, the spheres are aligned horizontally and vertically such that each sphere is in contact with 4 other spheres. So, the coordination number is 4. If we call the first row as A-type row, the second row being exactly same as the first row, so it is also called as A-type. If we keep on placing such similar rows one above the other, then such an arrangement is known as AAA type of arrangement or square packing. Hexagonal close packing. In this type of packing of spheres, the second row of spheres is placed in a staggered manner such that the spheres fit in the depressions of the first row. If we call the first row as A-type, then as the second row is different from the first row, it can be called as B-type. Now, if we place a third row above the second row in the similar manner, we will observe that the third row spheres are aligned with those of first layer, and each sphere is in contact with 6 other spheres. So, the coordination number is 6. Similarly, on placing the fourth layer, we will observe that the fourth row of spheres are aligned with those of second layer. Hence, this type of arrangement is known as ABAB type of arrangement or hexagonal close packing. If we compare square close packing with hexagonal close packing, we will observe that empty spaces are less in hexagonal close packing than compared to square close packing. Now, what are these empty spaces and what role do they play in packing efficiency? The empty spaces in between the spheres are known as voids. These voids are responsible for decrease in packing efficiency of the solid crystal. More the number of voids, less is the packing efficiency of the crystal. Now, you must be wondering what is meant by packing efficiency. We have discussed about this in later part of the section. Now let us study about close packing in 3 dimension. 3-dimensional close packing from 2-dimensional square close packed layers. This type of packing is obtained by placing 2-dimensional square closed packed layer above the first one, such that the spheres of the second layer are exactly above the spheres of the first layer. In this arrangement, the spheres of both the layers are perfectly aligned horizontally and vertically. On arranging layers one after the other in this pattern, we will observe that each sphere is in contact with 6 other spheres. 4 from the same layer, 1 from the layer above, and 1 from the layer below that sphere. So, the coordination number is 6. If we call the first layer as A-type, and since all the layers are also of the same type, this kind of arrangement is known as AAA type of arrangement. On observing carefully, we will find that this arrangement has generated a simple cubic lattice and its unit cell is primitive cubic unit cell. Dimensional close packing from two-dimensional hexagonal closed pack layers. The three-dimensional hexagonal closed pack structure can be obtained by placing two-dimensional hexagonal structures one layer above the other. Placing second layer over the first layer. Let us take a two-dimensional hexagonal closed packed layer A. Notice this layer has triangular voids. Place a similar closed packed layer in such a way that the spheres of the second layer are placed in depressions of the first layer. As the spheres of the second layer are aligned differently as compared to the first layer, so let us call this layer as B type. On observing, we will notice that not all the triangular voids of the first layer are covered by the spheres of the second layer. This gives rise to a different arrangement and different voids. Voids. There are two types of voids: tetrahedron voids, denoted by T, octahedron voids, denoted by O. Let us study how these voids are formed. When we place a closed packed layer above the depressions of the first layer, we will notice that at some places the triangular voids of the first layer are being covered by the spheres of second layer. At such places, a type of void is formed. This type of void is known as tetrahedral void, T, since a tetrahedron is formed by joining the centers of the four surrounding spheres. While at other places, we will notice that the triangular voids of the first layer coincides with the triangular voids of the second layer, such that their triangular shapes do not overlap. At such places, another type of void is formed. This type of void is known as octahedral void, O, since an octahedron is formed by joining the centers of the six surrounding spheres. Now, in case we need to calculate the number of tetrahedral and octahedral voids in a crystal structure, then just knowing the number of spheres will serve the purpose. Suppose there are n spheres in the crystal structure, then the number of octahedral voids generated is equal to n. The number of tetrahedral voids generated is equal to 2n. Placing third layer over second layer. Now let us place third layer over second layer. Stacking of third layer over second layer can be done in two ways. First, by covering tetrahedral voids. Second, by covering octahedral voids. By covering tetrahedral voids. The tetrahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer will get exactly aligned with the spheres of the first layer. So, if we can call the first layer as A type and the second layer as B type, then the third layer will also be A type. As the pattern of spheres is repeated alternately in other layers, so this pattern is known as AB-AB pattern, and the structure formed is known as hexagonal close packed HCP structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So the coordination number is 12. Covering octahedral voids. The octahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer are not aligned with the spheres of either first layer or second layer. So, if we call the first layer as A type and the second layer as B type, then this third layer will be C type. Now, if we place the fourth layer over the octahedral voids of the third layer, then the sphere gets aligned with the spheres of the first layer. Thus, this pattern is known as ABC type, and the structure formed is known as cubic close-packed CCP or face-centered cubic FCC structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So, the coordination number is 12.
Okay. The reason I was doing all that writing up there is because I've watched this thing dozens of times, trying to figure out what the relationship is between this closest packing model and our unit cells. And it looks to me like when she got to the hexagonal close packing, where you cover either the tetrahedral voids or the octahedral voids, you end up with the same coordination number for both of them. And which tells me that they're both face-centered cubic. But she only identified face-centered cubic for this one. All right. This slide talks about similar topics. This is an ABAB type, hexagonal close packing, looks like to me. This one, hexagonal close packing. So we're identifying that name with this one. Yep. And this one, ABCA, we're identifying cubic close pack. We're making a distinction there between those two. And this one is definitely face-centered cubic. And I'm still wary that may also be face-centered cubic, because that's the only unit cell that had a coordination number of 12. All right, the simple cubic had a coordination number of 6, and then the body-centered had a coordination number of 8, and then the face-centered cubic had a coordination 12. Okay, so hexagonal closest packing, the ABA, this one, in that diagram, is saying that we have a face-centered, it looks like face-centered cubic to me, doesn't it? Yeah. So I think we're onto something here. I believe they're both face-centered cubic, and identifying only this one as face-centered cubic is misleading. All right, there's a cubic closest packing unit cell, coordination number 12, just like we saw in the video. And this is where we calculate the number of bodies in each cell. or a total of 4. Face centered cubic has a total of 4. We're going to use that information to solve a problem. Well, not in 5 minutes, but we will eventually. Simple cubic, face centered cubic. So simple cubic has 1, face centered cubic has 4, and body centered has 2. All right, now if we're going to use the unit cell to tell us something about the substance, we need to know how to calculate the volume of the unit cell based upon any information we can get from the individual atoms. For the simple cubic structure, the length of an edge on this cubic arrangement, right, if we have one here and one here touching it, then the length of this edge is 2 times the radius. So if we have just metal atoms and we know the radius of the atom, then the length of that edge is just 2 times the radius. So, and we just cube that value and you get the volume of the cube. Right. If we have a face-centered cubic, right, now we have half of one here, and then we have one here and one here, one here and one here. We want to know what this length is right here based upon the radius of each one of those. So that requires a little trigonometry, and I've got explanations for this in Brightspace, right, if you want to look and see how it's done. But the end product, the length on that edge is equal to the radius of the atom times square root of 8. And these values are in useful information. Right? Every one of those review documents has pages at the back. You guys already know this. Has pages at the back with useful information in it. And if the useful information is in that review document, it will also be on the test. So just learn how to use it. If you do enough of them, you're going to memorize it anyway. Okay. For a body-centered cubic, so if this is in the center, right, then we have another calculation, and this is, or see, I don't even have it. 4 divided by, what's it, square root of 3. So that gives you this distance. On the edge of the cube. Now, how will we use that information? If we wanted to calculate the density of silver, and we know that it's a cubic closest packing, which leads to a face-centered cubic unit cell, and we didn't have to calculate the edge of the cell, that's given to you. But if you knew the radius of the silver atom, you could use the face-centered cubic formula and calculate. It's 409 picometers on an edge. So what's a picometer? A picometer. Well, let's see. Millimeter is 1,000th of a meter, right? And then let's see, micrometer is 1,000,000th of a meter, and a nanometer is 1,000,000th of a meter, and a picometer is a 1,000 billionth. What would that be? Not a trillionth. Billionth? Trillionth would be 10 to the minus 10. I can't remember. But that tells you how to convert that value to a unit that's going to give you eventually grams per cubic centimeter. That's density. So the measured density is 10.5 grams per cubic centimeter. Can we calculate that? Well, if it's a face-centered cubic, that means there are 4 silver atoms per unit cell. And we know the edge, so we can calculate the volume. We just cube picometers, and then we convert picometers to cubic centimeters. And then there's the value. And then we calculate the density. Right? How much does 4 atoms of silver weigh? Right? This is a dimensional analysis problem. You say 4 atoms at 107.9 grams per mole. How many moles is 4 atoms? Right? So that's where this conversion comes in. And then we divide the whole thing by the volume. And calculated, we get 10.5 grams per cubic centimeter. So it agrees with the measured value. All right. All right, I'm out. I'm officially out of time. But my first semester students know what to do when I get long-winded. If you have to go somewhere, go. And I'll continue to record and post it on Brightspace. But if you can stay around, you're welcome to. So these are the bonding models for metals. We looked at that example of a metal, and what do they call it? Not distributed, but dispersed. Electron. Let me go back and see. Use the right terminology. There it is. Delocalized covalent for metals. Okay. These are the theories that led to that. First theory, this is in chronological order. The first theory was the electron C model. And all it said was that you've got these nuclei of metals, and they're surrounded by electrons. And they're just kind of floating in that sea of electrons. Well, that may be a useful concept, but it doesn't give you a lot of information. That's what it would look like, right? The C model, the electron C model. It's kind of like the plum pudding model for the atom. That didn't last very long. Then when the molecular orbital model came along, now we got a better handle on things. Because the molecular orbital model, did you guys get that in your first semester? Molecular orbitals?
I can't,
Okay.
it's been like a few years.
Okay. Basically, the molecular orbitals were preceded by the localized electron model, where you're saying that each atom owns its electrons, and it only shares them by overlapping orbitals with its neighbors. That only goes so far. In order to give a more complete description of any type of bonding between atoms, with the ability to predict energies of bonding, which is unique to the molecular orbital model. This model actually says all those electrons, once you form the compound or form the unit, all of those electrons belong to the collective. You know, it could be the communist orbital model. It's the electrons belong to the collective now. And you have energy levels, just like you do for individual atoms, energy levels that these electrons occupy in that molecular orbital situation. Well, if you only have 2 metal atoms, then the separation of the energy levels is significant. But as you increase the numbers of atoms in the substance, the gap between them becomes almost insignificant. So what that means is those electrons just take a tiny amount of energy and they'll move between levels, easy. They're still quantized, but the quantum is very, very small. We often refer to these in terms of what is the highest filled molecular orbital And then right above it is the highest unfilled molecular orbital. And the energy gap between those two is very small. Let's see. Oh, okay. So it forms a virtual continuum called a band. And that is an explanation for why metals are very good conductors of electricity and heat. Okay. When we put, now we're going to, up to this point, we've talked about substances that were made up of, were pure, and individual particles, atoms, or molecules. And there were nothing else, except for the ionics, right? Then there was that's the crossover. But if we focus on metals now, and you get a structure of, you have metals, and you want to add something to them, call that alloying. You add something to your metal and make an alloy. It's a mixture. There are two types of alloys that we can identify. One is a substitutional alloy, in which the added substance replaces some of the solute atoms. Okay, it substitutes for them. Brass is a perfect example. It's mostly copper atoms. But every now and then, we replace them with nickel. So in order to do that, the nickel atom has to be roughly the same size as the copper atom to fit into that lattice. The other type of alloy is the interstitial. Remember when we were talking about the tetrahedral and the octahedral voids? Those voids are small, but there are some atoms that will actually fit in those voids. And the perfect example of that type of alloy is steel. When you add carbon to iron, iron has its arrangement and has the voids. And in those voids, we're going to stick carbon atoms. And what that does is it forms a bond with the metal atoms on all around it. And the effect is that the iron atoms can't shift. They're locked in place by that carbon. That's what makes steel harder than pure iron. Pure iron you can scratch with your fingernail. It's very soft. But steel is another story. Okay, those are two examples. Copper and zinc. Copper and zinc is no, copper and tin is bronze. Copper and zinc might be a class of brass. I think brass now can have both nickel and zinc in it. And then below you have the iron and carbon, where the interstices are occupied by some carbon atoms. Here's the difference between diamond and graphite. Remember, at the very beginning of our first semester, we talked about elements and the forms that they could occupy. And we said that some elements can come in different structures called allotropes. And we used carbon as an example. Like graphite is one in which the covalently bound atoms form hexagons in plates. And then there are weak forces between them. These would have to be London dispersion forces between the layers, right? So they slide past one another really easily. So graphite is often used as a dry lubricant. Since it's not wet, it doesn't pick up dirt and dust, but it still lubricates the movement of parts. Whereas diamond is that network solid with covalent bonds in all directions. So it's the hardest known naturally occurring substance. On a Mohs scale, it'd be 10. Let's see, Mohs, a diamond is 10 and talc is 1. And then you have great. Okay, for diamond, there's a huge gap between the filled molecular orbitals and the empty molecular orbitals. So it takes a lot of energy to promote electrons into that empty MO. What that means is it can be measured in terms of thermal conductivity. There you go. I better write it down or I forget it again. Thermal conductivity for diamond is very high because it takes a lot of energy to promote electrons into the higher empty molecular orbital. So gemologists use a device that can measure the dissipation of heat into a substance. They just touch it. And the device measures how much heat is transferred over a certain amount of time, and it comes up on a scale. The thermal conductivity of diamond is very, very low. It does not conduct heat very well. So if you take a gem to a jeweler and you want to know, is this, I'll say a blue diamond, or is this a tanzanite? Because they look a lot alike. Well, they'll put that device on it and say, all right, the thermal conductivity on this is pretty high, right? It's probably tanzanite. Or you can be like my wife, who got a what was supposed to be a tanzanite from a friend, and all we had to do was pay for shipping. It came to us, and we took it to the jeweler and showed. We were looking for a setting because it was a free stone. And he said, "Oh, that's a beautiful diamond you had there." I said, "Wait, that's not a diamond. That's supposed to be a tanzanite." So they got their device out and they put it on that extremely low thermal conductivity. They said, "You got a blue diamond there, folks." So we left it with them, and I immediately called my insurance company and said, found out how much it was worth and got a certificate. And then I called my insurance company and said, "We'd like to add this to our policy." And then we mounted it, and she wears it sometimes. But most metals, the gap between the two is very small. So they will have very high thermal conductivity. Now, when we look at the graphite again at the atomic level, we find that we have these unused p orbitals. Right? We noticed that with benzene. Remember the benzene ring? It had the benzene would be like that. And typically we draw it like this. But in fact, that says that the bond lengths and energies are different, but they aren't. They're exactly the same bond length all around. So what sometimes we do is put a circle in there to represent all of them equivalent. Well, each one of these carbons is attached to 2 carbons and a hydrogen. Okay? So that means what? 3 groups means trigonal planar, right? Trigonal planar. And hybridization would have to be sp2. We're only using 2 of the p orbitals along with the s to hybridize into 3 equivalent hybrid orbitals. That leaves 1 p orbital for each carbon free. And they interact with one another and form this delocalizing cloud above and below the plane of the graphite. Now, what it doesn't show you here, because we're showing you the p orbital separate, it doesn't show you the system until you get to the B scale. And that would look like this or that. So within the plates, they're very stable, but between there's opportunity to move. Let's see. I should be getting close to the. Oh, we still have to talk about colligative properties. Okay. I'm going to lose my audience if I keep talking. What's a ceramic? A ceramic is operationally defined. In other words, a ceramic is what you say it is. Right? I had an advisor when I was working on my PhD tell me I had this procedure I was using to differentiate certain types of manganese in the soil. And I said, how am I going to reference these things? He says they're operationally defined. In other words, they're whatever you want them to be. So a ceramic is typically a non-metallic material. So it comes from this side of the table. Now you can have metals in ceramics, but the core, the base of the material is non-metal. They're very strong in compression, but they're very brittle. So if you have a shear force on them, they'll crack. They're resistant to heat, and most of them are resistant to chemical attack. And most of them actually are made from different types of clays. So fine china is a ceramic. Stoneware is a ceramic. Right? The tiles on the space shuttle were ceramics. The tiles on the on SpaceX Starliner, not Starliner, Starship. I forget what they call it, but they've got those black tiles on the outside. They're ceramics. They're very heat resistant. They protect the underlying structure of the capsule. And they're made from clays by firing. You heat them to a very high temperature and they change their crystal structure as a consequence. What's a semiconductor? Well, when you study electricity, right, if you're going to be an electrician, you're only concerned with conductors and insulators, right? When you're wiring house, you want the copper wire surrounded by an insulator so it doesn't ground or shock you. But when you get into electronics, like computers and cell phones and that type of thing, we're dealing with semiconductors. That's the space in between insulators and conductors. They're slightly conductive under certain circumstances, which means we can control it. If you can control the movement of electrons, you can control information transfer. So that's the draw of semiconductors, is the ability to turn them on and off. And that's where you get the ones and zeros, the binary code. Okay, we have two types of semiconductors. One's the N type and one's the P type. N type just simply means there's an excess negative charge in the semiconductor. And the P type, of course, by inference, there's a deficiency of negatives in the structure. And the way you make it is you have a pure substance, a pure non-metal substance. Most semiconductors are based upon silicon. So we produce absolutely pure silicon. And if I've never seen it personally, but I've seen videos of the production of pure silicon, and it comes out of this vat. It's about that big around, and it's about 10, 12 feet tall, a solid ingot of pure silicon, and then they slice it. So you got your silicon as the base, and then you dope it with a certain amount of other elements. Now, for silicon, if the elements come from the right side of silicon, they have more electrons in them than silicon does. So that gives you the N type. And if you dope them to the left of silicon, then that gives you the P type, because they are deficient in electrons. To understand how the electrons move, we find that the conduction band and the filled molecular orbitals are not as far away as diamond, but they're not as close as metals either. They're in between. So it does take some energy to get those electrons to move. And believe me, for either one, it's the electrons that move. But for conceptualizing the semiconductor, we often say, all right, for the N-type, it's easy to think of electrons moving. But for the P-type, we think of the holes moving, the empty spots moving, right? But whenever this one, a positive moves over here, a negative goes the other direction. Okay, so this is an example of an N-type where arsenic is doped. Arsenic's to the right of silicon. And the one below it where boron is doped is to the left of silicon. That gives you a P-type semiconductor. Okay. How about ionic solids? Ionic solids are like table salt. And even though table salt has ions in it, if you put a positive and a negative electrode on either side, attach it to a power source, you will get no current. The solid, those ions are locked in place. They can't move. So these ionic solids are mostly, or actually, I could say probably they're all insulators, electrical insulators. The only way that you can get them to conduct electricity is to melt them or dissolve them in some liquid to free up those ions. But they're bound together by very strong electrostatic forces. And they are generally have high melting points, very high temperatures required to melt them. Now, what's responsible for the melting point? What would increase or decrease the melting point for an ionic solid? Well, it all goes back to the attractive forces between the ions. And there are two things involved. One is the size of the charge on each ion. So if you have magnesium oxide, where magnesium is a 2+ ion and oxygen oxide is a -2, that's a stronger attraction between a +2 and a -2 versus sodium chloride, which is a +1 and a -1. And so you get that effect of the size of the charge. And then there's distance, right? So the size of the force of attraction is dependent upon the square of the distance between them. So as you get them closer, the force increases. So if you can get those ions closer together, then the force increases. And in this case, magnesium oxide wins in both situations, the size of the charge and the closeness of the ions. So the attractive force for magnesium oxide is much, much greater than sodium chloride. As a consequence, the melting point of magnesium oxide is also higher than sodium chloride. It takes more energy to break that bond. All right. This discussion was part of that video, so we don't have to spend a lot of time on it. If you've got a single layer of packed spheres, you can have this trigonal hole, and it's based upon tying the centers of the spheres together. You get that triangular hole. And the size of that hole dictates, especially for ionic solids, which is going to be the largest sphere in an ionic solid. It's going to be the anion, right, with the extra electrons. That makes them balloon out. And then the cation has lost electrons, so it shrinks. So the type of physical arrangement of the cations and the anions depends upon the size of that hole. If the anions give you a certain size hole, like this trigonal hole, then the cations have to be small enough to fit in it if we're going to use that model. Now, that was only 2 dimensions. For 3 dimensions is actually where we're headed. The tetrahedral hole, in this case, is small, but not too small, and the zinc ions fit into that hole. So the sulfide ions make the tetrahedron, and the zinc fits in that hole. If we have this model, right, where the octahedral holes are covered by the layer above them, actually they form the octahedral hole, excuse me. We have the, yeah, that's right. So what is the size? This is a little misleading because trigonal is two-dimensional. Tetrahedral and octahedral are three-dimensional. So I think the comparison there is apples and oranges, right? But we do know that octahedral holes are bigger than tetrahedral holes. So that will have a bearing on the type of structure that your ionic solid would occupy based upon the size of that hole and the size of the cation that would fit in it. All right, this comes straight out of your book, so I'm not going to spend a lot of time on this one. Now we're going to look at some properties and associate them with intermolecular forces. The first one has to do with vapor pressure. If I put a liquid in a container, in this case, we're using a flask, Erlenmeyer flask. Put a stopper in it, and we have a liquid down here. When we first put that liquid in there and stopper it, what's going to happen? Atoms are going to move one direction, right? Because there are none up there, right? So these atoms are going to, depending on the strength of the intermolecular force, they're going to move from the liquid into the gas phase. And if the strength of the attraction is low, more of them are going to go up faster. So ethanol, our example, ethanol would move at a certain rate and release molecules. Dimethyl ether, being the same molecular formula as ethanol, but a different structure, has a lower attractive forces. It's a nonpolar. More of them would move quicker. So once you get enough of them up here, then some of them start returning. And the equilibrium situation is where the rate of evaporation equals the rate of condensation. And at that point, if the vessel is closed, we develop a pressure, a head pressure above that liquid. This is vapor pressure. And vapor pressure gives us a clue as to how strong the intermolecular forces are. The higher the vapor pressure, the weaker the intermolecular forces. Let's get that. This mentions equilibrium. I just told you that one already. So what's the vapor pressure of water at 100 degrees C? The vapor pressure of water at 100 degrees C is 1 atmosphere. Because that's the boiling point at 1 atmosphere pressure. This illustrates in a sort of a barometer the difference in vapor pressures for these different compounds. Water's in the second one from the left, and it pushes down on the mercury column a little bit, 24 torr at a given temperature. I think this is probably 25 degrees Celsius. And then ethanol, you know, the drinking alcohol, if you put a little bit of that up there and let it evaporate, it will push down even harder, 65 torr. And if you put the analog to, actually, that ether in the last one is not dimethyl ether, that's diethyl ether. But we're illustrating the influence of intermolecular forces on vapor pressure. So the intermolecular forces of all ethers are very low. So more of it vaporizes and produces, in this case, an extremely large vapor pressure at 25 degrees, 545 torr. Okay, so this is the one property of substances that runs let's see, as the intermolecular forces increase, the vapor pressure goes down. They're inverse. The rest of them, if the intermolecular forces increase, the measured quantity goes up, like melting point goes up, boiling point goes up. But with vapor pressure, if the forces increase, the vapor pressure goes down. And these are examples. I'm not going to spend a lot of time here. It just shows you that at any given temperature, depending on the intermolecular forces, you get a this is the vapor pressure at a given temperature. You don't have to remember this. This is the derivation of the Clausius-Clapeyron equation. All right, so you can look at that at your leisure. If we look at at this equation, natural log of the vapor pressure equals the enthalpy of vaporization divided by R. Let's see, this is negative, isn't it? Yeah, it's negative. And this is times 1/T plus some constant. Then what that tells you is if this is Y and you plot that against this X, then you get a straight line with this slope. And by doing that, at different vapor pressures measured at different temperatures, you can calculate the heat of vaporization for that substance using this equation. The other way to use it is an integrated form. This Clausius-Clapeyron equation. If you have the vapor pressure at one temperature and the vapor pressure at the other temperature, and you put the temperatures in there, in this equation, then you can directly calculate the heat of vaporization without having to go to the graph. All right. So this is an example. If your vapor pressure of water at 25 degrees is 23.8 torr and the heat of vaporization of water is 43.9 kilojoules per mole, what's the vapor pressure of water at 65 degrees? Right. So we went back to, we have heat of vaporization, we have two temperatures, we have vapor pressure at the lower temperature. So if we go back to the Clausius-Clapeyron and we put them in the high temperature here, high temperature there, low temperature there, and this is our unknown because we know what the vapor pressure is. And notice it's missing a negative. I think that's correct. Yeah. Then we can solve for the unknown and find out what the vapor pressure is. And if we do that, we find that the vapor pressure increases from 23.8 to 194 torr by increasing the temperature 40 degrees. What's the heating curve for water? We can represent the heating curve in this way. If we have temperature on the Y scale and added heat, as we add more heat from left to right in the X scale, then we find, first of all, if we start with the solid at, in this case, minus 20 degrees Celsius, then we add energy. And what's happening is the temperature is increasing as we add energy. And it's still ice. It's still solid. Once you get water, once you start to break those intermolecular bonds, all the energy goes into that process. And no more energy is used in heating the substance. So the temperature flattens. It stays at zero until all the ice is gone. So that's why in the first semester, if you wanted to know the melting point of water, we measured, I think in the first lab, we had ice and water together and we measured it. As long as you have ice and water together, the temperature is constant. That's why we did that. Then once all the ice is gone, you can start heating the liquid water again. And that gives you the green part of the curve. Once you get to the boiling point, now a similar situation, all the energy is going into breaking those intermolecular bonds and making a gas. and the temperature remains constant until all the liquid water's gone, and then you can superheat the steam. Okay, which would you predict to be larger for a given substance? The heat of vaporization or the heat of fusion? The heat of fusion is the energy required to melt a solid. That's what that means. And the heat of vaporization, of course, is going from a liquid to a gas. So which one would be larger? Which one has to overcome the most force? Think about, I'm sorry?
Vapor?
Yeah, vaporization is much, much higher value. The solid going to a liquid, all you have to do is just break the force enough so that the molecules can slide past one another. But with vaporization, you've got to take that liquid and break the bonds completely so that those individual atoms can be independent players. Okay, there's another way to represent these phase changes, and it's called a phase diagram. And I'm going to point out triple point, critical point, and equilibrium lines. That's the way it's made. This is a very, very simplified version. There are phase diagrams of materials that have a dozen lines in them. And they mean something to engineers, but we're going to keep it real simple. This is carbon dioxide. So what you find is you've got three areas of this graph, and one area references solid, one references liquid, and one references gas. And the lines that separate them are those phase equilibrium lines. So at that line, for the x-axis has temperature, the y-axis has pressure. At that combination of pressure and temperature on that line, you have both liquid and gas, or liquid and solid, or solid and gas, depending on where you are on the lines. If you're in the bulk of the solid or the liquid or the gas, then at those temperatures and pressures, that's all you have. Right? You have no other phase but that. Now, where these lines meet, the triple point, is a specific pressure and temperature where all three phases exist together. Solid, liquid, and gas, that's at the triple point. And then the last defining characteristic of this phase diagram is the critical point. When you follow the liquid gas equilibrium line out, it comes to a point where it stops, which means that beyond that point of temperature and pressure in that region, you've got a fluid, but you can't tell it's not distinct liquid or gas. It's both. We call that a supercritical fluid. And the supercritical fluids, particularly with carbon dioxide, are used industrially as extractants. The best decaffeinated coffees are made by using supercritical fluid, carbon dioxide. They turn it into that supercritical fluid. They mix it with the ground coffee or the whole beans. It would work there too. And the interesting thing about supercritical fluids is there's almost no resistance to their movement through membranes. They will go into the cell, lickety-split, and come out with whatever they dissolve. We had a device in my previous life. It was a supercritical fluid extractor. And it was a machine set about like this. And we had a tank of carbon dioxide over here, and the system would pressurize it up to a certain pressure, and the temperature would be increased to a certain level, produce the supercritical fluid, and then it would be injected into our sample container where we had usually plant tissue. And it would extract those things, and we'd bleed off the supercritical fluid over here. And when you let off the pressure, carbon dioxide goes, it's gone. And all you have left is this pristine extractant. The nice thing about it is it gets everything out of the cell. Plus, it doesn't damage it at all. I mean, this material that you've just extracted is is the same, exactly the same as you had inside the cell. Other extracting procedures like Soxhlet reflux, where you heat the methanol and it refluxes into a cellulose thimble with your sample, fills it up, extracts it, and then the siphon takes it off back down in and heats it up again. That amount of heat for as long as you have to do it will alter the metabolites that you're interested in. So supercritical fluid is very nice for that, but we can only do one sample at a time. If you have a Soxhlet setup, you can do 16 or 18 or 20 at a time. So it depends on the analyte that you're interested in determining. Now, the phase diagram for water is a little wonky. Notice that in that previous one, the slope of the line between solid and liquid is positive. Whereas with the solid liquid line for water is negative. So what that means is at a given temperature where that X is located, if you increase the pressure at that given temperature, then you will go from solid to liquid rather than from liquid to solid. So pressurizing our liquid at that temperature doesn't make it into a solid mass. It turns a solid into a liquid. For the longest time, that was the explanation for ice skates working the way they do. Because if you put all your mass on that tiny blade, the pressure increases to the point where it was assumed that we converted solid ice into liquid, and liquid allows you to, reduces the friction. But there have been other experiments to try to test that theory, and it turns out to be wrong. So the reason your steel on ice slides so easily is because the coefficient of friction between steel and ice is very, very low anyway. But it's an interesting phenomenon. Okay, so as intermolecular forces increase, what happens to each of the following? Each of the following is going to increase as you increase the forces. Boiling point goes up, viscosity goes up as you increase the forces between the molecules, surface tension increases, it costs more energy to melt it. Freezing point, it costs more to energy to well, enthalpy of fusion and freezing point. The temperature, higher temperature, excuse me. Vapor pressure, that's the one that runs the other direction. And heat of vaporization also goes up. So the only one that decreases with increasing molecular force is vapor pressure. That's it.